Take a look at Relations and Functions Lesson 8, where we're looking at the first part of function notation. So, a function was defined in mapping notation as follows. A function from a set from the domain to a set from the range is a relation of each element, in which each element of the domain is related to exactly one element of the range. So that means that if I know what the domain is, I can only have one possible range value that actually matches. If the function f maps an element x in the domain to an element in y, then we write the function is going to be x is my input, I do a process, and then I get an output of y. If I have the function f of x, where x has an input and the output is going to be 2x plus 3, then I could pick a number. In this case I picked 5, where I'm going to say 2 times 5 plus 3. So if I have an input of 5, I'm going to have an output of 13. We say that under the function of f, the image of 5 is 13. We can also say the value of the function is 13 when x is equal to 5. So, when we're using function notation, in most math courses, function notation is used to replace the mapping notation, where we're just going to list it as f and then these brackets x, where that just means f of x. So f of x is going to equal, and then we're going to say what the process is. We call this function notation because it's saying that what the value on the left-hand side is dependent on whatever the variable is inside of those brackets. So that's going to be my input, and then I'm going to get the output when I complete the process. We showed that above that under the function of f, the image of 5 is going to be 13, so you'd write that f, when the input is 5, is going to have an output of 13. So we can see the mapping notation method for that, we can see the function notation, or we can see if we just had a graph, because we know that after the function is done, the output is going to be my y values. So f of x, when I complete my function, is always going to equal y, unless I'm using different variables. So a couple of things to note. F of x does not mean the value of the function multiplied by x. The name of the function is f. It doesn't necessarily have to be f. That is a standard one that we use, but I could also say g of x. I could say h of x. If I have multiple functions, I'm going to use more letters. Values of the independent variable represent the inputs on the horizontal axis. Value of the dependent represent the outputs on the vertical axis if I'm graphing the results. How does that look in practice? Well, here we're given a function. F of x is equal to x squared plus 5. And then we have a different function, g of x is equal to 4 minus x. For the first one, it's replaced my x variable with a 3, which means that's what I'm actually going to put into the function. I'm going to use brackets to replace my x and say that's going to be, instead of x squared, 3 squared plus 5. And when I plug that in, that's going to give me 14. In the second case, it says g of 1. Well, I'm going to use the other function in this case because it's using the g function. And I'm going to replace x with bracket 1, which is going to give me 3. For example, c, it's the f function. So I'm going to say negative 2 squared plus 5. And negative 2 squared is going to give me 4, so this is going to be 9. For example, d, it's using the g function. 4 minus negative 2 is going to give me 6. Now for e looks a little bit more complicated because it's actually using both functions. So in this case, I would actually say that I'm going to put in the 1 function, and I'm going to have 0 squared plus 5, And then I'm going to subtract from that the complete second function, 4 minus 0. I can simplify this. 0 squared is just 0, so it's just going to be 5 minus 4 minus 0 is just going to be 4, and it's going to give me 1. If I'm looking at the second cases, it's just showing us the different ways that we can state this. So the first one is the exact same way as we were doing in the previous examples. It gave us our variables, and it said f of x is equal to 5x to the power of 3 minus 2x, and then it just made the stipulation that xer, which means x can be any real number, a whole number, a natural number, an integer, a rational, or an irrational. When it wants us to determine these things, well, the first one I'm going to say this is going to be equal to 5 times negative 3 to the power of 3 minus 2 times negative 3. When I plug that in, I get negative 129. When it says the value of f when x is equal to 2, it literally is stating the same thing that the first one did, whereas just this would be the same as f of 2. And I'm just going to replace the variables again. 5 bracket 2 to the power of 3 minus 2 bracket 2, and that's going to give me 36. The image of 7 under f, well, 7 under f just means that I would have that f to the 7 again, once again, just a different way of writing the same thing. And I'm going to say that this is going to equal 5 bracket 7 to the power of 3 minus 2 bracket 7, which is going to give me 1701. Now, it's not always going to be an actual number. Sometimes I can just replace it with a different variable, which means in this case, if I said f of a, then the x's are just going to get replaced with a's. And I'm just using a different variable to represent the function. If I'm looking for an expression of f of 2x, I'm just going to replace every x with bracket 2x and then see if I can simplify. So I'm going to say that this would be the same as 5 bracket 2x to the power of 3 minus 2 bracket 2x. Well, 2x to the power of 3 is going to be 2 squared, or 8, and then x to the power of 3. And negative 2 times 2x is going to give me minus 4x. And then when I multiply the 5 into the left-hand side, 5 times 8 is going to give me 40, x to the 3 minus 4x, and there's my new simplified equation.